A-Level Chemistry, Paper 3, Specimen, version 0.5. Ethanol can be oxidized by potassium dichromate, so ethanol will then turn into ethanal and continue to make ethanoic acid, if heated for a prolonged time, a process called reflux. In order to ensure that the oxidation to ethanoic acid is complete, the reaction is carried out under reflux, and I've drawn a diagram on the right hand side. You can see that there's a flask and then there's a condenser with cold water passing through it. If you were to stopper the flask and heat it up, the pressure would crack the flask or pop the stopper off the flask. So we need a method of heating this for a prolonged time, having it open to the air so that the pressure can be released, so that there's not too much of a build-up of pressure, and yet not leave the liquids evaporating out into the open air and ending up with losing the mixture. So describe what happens when a reaction mixture is refluxed and why it is necessary in this case for the complete oxidation to ethanoic acid. So the mixture of liquids are heated in the flask to a boiling point for a prolonged time, but any vapour, any gases that escape from the liquid mixture are then cooled and condensed by the cold water condenser and returned into the flask as a liquid. Any ethanol and ethanol that initially evaporates are then returned back to the flask and can continue to be oxidized to ensure that there's complete production of ethanoic acid, so that the reaction, the oxidation, completes through to the ethanoic acid stage. You can also add anti-bumping granules into the flask as well to prevent large bubbles from forming. Write an equation for the overall oxidation of ethanol into ethanoic acid. So remember, a half equation always involves electrons. If I've got an E-, that is, if I've got ethanol and ethanoic acid, it's never going to balance. If you look for a start, there's two O's on the right hand side and one on the left. You can always add H pluses and H2O to any half equation to get it to balance. So clearly we need an extra O on the left hand side, so the only option of these two, H plus and H2O, is an H2O that's got an O. So if I add an H2O onto the left hand side, now the O's balance, but unfortunately the H's don't. I've got 3, 4, 5, 6, 7, 8 H's on the left and only 4 on the right hand side. So I need 4 extra H's on the right hand side. That's when I use H plus. So I'll put H plus on the right hand side and I'll need 4 of them. Now all the H's and the O's balance. Unfortunately I've got 4 pluses on the right hand side and I've got no pluses on the left hand side, and that's where the electrons come in. My electrons can balance that by putting 4 electrons on the right hand side. So CH3CH2OH plus H2O makes CH3COOH plus 4H plus 4 electrons. Question 1.3. The boiling points of the organic compounds in a reaction mixture are shown below. So I've got ethanol with the lowest boiling point, then I've got ethanol with the next lowest boiling point, and then I've got ethanoic acid with a boiling point of 118. Describe how you obtain a sample of ethanol from a mixture of these compounds. Include either a diagram or a written description. Well, I've drawn the diagram to start off with. I could only find a diagram of an oil bath, but you could have a Bunsen burner with an arrow with heat going up underneath it, and then I've got a flask, and then I've got a thermometer. In this section of apparatus called a still head. So this piece of glassware here is called a still head, which contains the thermometer. Then I've got a condenser with cold water going through it, and then I've got a collection vessel here, and I've cooled the collection vessel with cold water to ensure that we get a maximum yield of the product here, that it comes down and condenses and turns into a liquid here rather than remains as some kind of gas. So what could we do? Mixture is heated in a suitable flask, fine, with the still head containing the thermometer. That's this piece of glassware here. The water cooled condenser is connected to the thermometer to the still head piece of glass here, and a suitable collecting vessel is put at the bottom of the condenser. You collect the sample at the boiling point of ethanol, so you'd heat it up to above 21 degrees C but less than 78 degrees C, and you could measure that with the thermometer, and you'd cool the collection vessel as well to try and reduce any evaporation of ethanol from the mixture to maintain it, try and maintain it as a liquid. Question 1.4. Use your knowledge of structure and bonding to explain why it's possible to separate ethanol in this way. Well, remember, you're separating ethanol from ethanol and ethanoic acid. Well, ethanol and ethanoic acid each have an O bonded to an H. If you have an O bonded to an H, or an F bonded to an H, or an N bonded to an H, then the difference in electronegativity between the O and the H is large, and therefore you get a large polar bond, a large delta plus and delta minus. And therefore in ethanol and ethanoic acid, the intermolecular hydrogen bonds that you get are going to mean that they have a larger boiling point than the ethanol. The ethanol doesn't have any oxygen bonded to an H. It has a carbon bonded to an H, so it has a polar carbon to oxygen bond and has dipole-dipole bonding, but it's less than the hydrogen bonding, the strong hydrogen bonding, intermolecular hydrogen bonding in ethanol and ethanoic acid. So the answer is that ethanol and ethanoic acid have hydrogen bonding, and that means that their boiling points are higher than the ethanol. They have higher boiling points than ethanol, it should say that. Okay, a student obtained a sample of liquid using the apparatus. Describe how the student could use chemical tests to confirm that the liquid contained ethanol and did not contain ethanoic acid. Lots of marks here, for 5 marks for 2 chemical tests. So how do you test for ethanol to show that it contains ethanol? Well, you use warm Tollens reagent. So add Tollens reagent, make sure it's warm. You need the conditions warm at A2. So at A level, you need warm Tollens reagent, and a silver mirror is made. Alternatively, you could add failing solution and it would make a brick red precipitate, but this is the more sort of normal test, regular test. Add warm Tollens reagent, a silver mirror test, and then it says did not contain any ethanoic acid at all. But you'd add sodium carbonate and you wouldn't get any bubbles. No bubbles or effervescence is observed. The word bubbles is fine. You can use the word effervescence if you want. It means the same thing. Question 2. Ethanol and ethanoic acid are reacted to make an ester, ethyl ethanoate and water. It's an equilibrium reaction. A mixture of 8 times 10 to the minus 2 ethanoic acid and 1.2 times 10 to the minus 1 ethanol is allowed to reach equilibrium. It looks as if we've not started with any ethanoic acid or water. The equilibrium mixture is placed in a graduated flask and the volume made up to 250 centimeters cubed of water. A 10 centimeter cube sample of the equilibrium mixture is titrated with sodium hydroxide. The ethanoic acid in this sample reacts with 3.2 centimeters cubed of 2 times 10 to the minus 1 moles of sodium hydroxide. So the very first step before we start unravelling this is that I've got a volume and a concentration of sodium hydroxide. So first of all we need to work out moles. We wouldn't be given a volume and concentration unless we needed to work out moles. So let's do that. Sodium hydroxide is titrated with the ethanoic acid. Concentration is 2 times 10 to the minus 1, or 0.2, equals moles. Concentration is moles divided by volume. Now I need to convert this volume centimetre cubed into decimetre cubed. A small unit like a centimetre cubed into a larger unit like a decimetre cubed, I divide by 1,000. So 3.20 divided by 1,000 is 0.032. Number of moles, 0.2 times 0.0032 is 0.00064. So that's number of moles of sodium hydroxide that I've got. What's it reacting with? Well, it's been titrated with this mixture. So when it's titrated with the mixture, it's going to react with the ethanoic acid. Sodium hydroxide is a base and it reacts with acid, so it's going to react with the acid. So sodium hydroxide and ethanoic acid will make water and a salt called sodium ethanoate. And 1 mole of sodium hydroxide will react with 1 mole of ethanoic acid. But I haven't got 1 mole of sodium hydroxide, I've only got 0.00064 moles of sodium hydroxide. So therefore 0.00064 moles of ethanoic acid are in the sample. I've just found out how much ethanoic acid is in the sample. Now when we take a sample, it means we're taking a small part from the mixture. We had 250 centimeters cubed of the mixture and we took 10 centimeter cubed. So 10 centimeter cubed, the sample of only 10 centimeter cubed contains 0.00064. So by a little bit of maths I can divide by 10 and 1 centimeter cubed would contain 0.00064. So 250 centimeter cubed, the original sample, multiplied by 250, there are 0.016 moles of ethanoic acid in the equilibrium mixture. Another way of doing it, if your maths is slightly stronger, is to work out that 10 centimetre cubed out of 250, divide 250 by 10, so 250 centimetre cubed is 25 times larger than the sample. Just multiply 0.00064 by 25 and you'll come out with the same answer. Now, this is where we need to do a little table. The little table, let's work out the little table. At the start, the ethanoic acid is 0.08 or 8 times 10 to the minus 2. It tells you that in the question. The amount of ethanol is 0.12 or 1.2 times 10 to the minus 1. There's no ethyl ethanoate and no mention of water either. So that's at the start. It's always helpful to lay it out like a table like this. Then at equilibrium, we've just worked out that there's 0.016 ethanoic acid made. 0.016 moles of ethanoic acid are in the equilibrium mixture. So this 0.016 is what we've just worked out. Now then, if I started with 0.08 moles of ethanoic acid and I've worked out that in the equilibrium mixture is 0.016, by subtraction I can work out how much ethanoic acid has been used up from the start to the finish. So 0.08 take away 0.016, I've used up 0.064 moles of ethanoic acid. So 1 mole of ethanoic acid reacts with 1 mole of ethanol to make 1 mole of ethyl ethanoate and 1 mole of water. So if I've used up 0.064 moles of ethanoic acid, I must have used up 0.064 moles, the same amount of ethanol, and I must have made the same amount, 0.064 moles of ethyl ethanoate, and the same amount of water, 0.064. So I've used up 0.064 moles of ethanol, and I've made 0.064 moles of ethyl ethanoate, and I've made 0.064 moles of water. Let's work out how much is in the equilibrium mixture then. The ethanol I started with was 0.12. I've just used up 0.064 moles of it, so I can work out how much is left, 0.056. I didn't have any ethyl ethanoate to start with, and I made 0.064, so that's how much I've got in the mixture. And the same for water. I didn't have any water to start with, I've got 0.064 moles of water made. The last bit, the Kc. The Kc is the concentration of ethyl ethanoate multiplied by the concentration of water, divided by the concentration of ethanoic acid, and divided by the concentration of ethanol. There's no numbers in front, there's just ones in front, so each of these concentrations are to the power 1. So that's my Kc, concentration of ethanoic acid multiplied by the concentration of water, divided by the concentration of ethyl ethanoate multiplied by the concentration of water, divided by the concentration of ethanoic acid, divided by the concentration of ethanol. Straightforward expression for a Kc from an equation at equilibrium. So let's have a look what I've got at equilibrium. Concentration of ethanoic acid, ethyl ethanoate rather, is 0.064, 0.064 for the concentration of water, divided by the amount, the concentration that I've got, 0.016 here, and 0.056 moles of ethanol. I could divide by the volume, 250 centimetre cubed, but because I'd be dividing by 250 centimetre cubed twice on the top of the equation and 250 centimetre cubed twice on the bottom of the equation, they'd all cancel out. So I'm just going to use the number of moles. The number of moles will work out exactly the same as if I'm converting each of these by dividing by 250 centimetre cubed. Another way of working that out is that I've got 2 moles of reactants, 1 mole of ethanoic acid and 1 mole of ethanol, and I've got 1 mole of ethyl ethanoate and 1 mole of water. If I've got equal numbers of moles of reactants and products, then I don't need to divide by volume. So I can just use these straight numbers without dividing by the volume at all. The volumes would cancel on the top and the bottom because there's equal numbers of moles of reactants and products. When I work all that out, it turns out to be 4.57. 2.2. A student obtained titration results given below. Complete the table 2. Well, all you need to do is subtract these values and make sure you do it to 3 significant figures or 2 decimal places, and it comes out as such. Calculate the mean titer and justify your choice of titers. So for the results to use, they need to be 0.1 apart or less, no more than 0.1 apart. Those are called concordant results. So 4.5 is far apart from the others, that's not surprising, it's a rough titration, and between these two, these are 0.2 apart, so they're too far apart. Those are 0.25 apart, so those are too far apart. Whereas titration 1 and titration 3 are 0.05 apart, they're within the limit of 0.1. So I'm going to use titration 1 and titration 3 and do an average of those two. I ignore all the other values. So 4.00 from titration 1, 3.95 divided by 2, 3.98. I've rounded it up so that I've got it to 3 significant figures or 2 decimal places. So I've not gone to 3.975. So I've rounded it up, so I've got it to the right number of significant figures, 3.98. And as I say, justify your choice of titers. All you need to do is say titers 1 and 3 are concordant, i.e. no more than 0.1 centimeters cubed apart. The pH ranges of 3 indicators are shown below. Choose a suitable indicator. So what I'm doing is I'm looking for the equivalence point. The equivalence point is where the pH rises very, very quickly. So it looks as if it's rising in this range here, between about 6 or 7, and around about 11, somewhere around that range. So I've got to try and find an indicator that works within that range. So my answer is 3.8 to 6.4. No, 3.8 is below where it's rising at 7, 6, 7, 6, 7 to 11, 6 or 7 to 11, 6 or 7 to 11. Could be bromothymol blue, I suppose. 6 is right on the limit. I probably want 7. 7 is where it's starting to rise quickly. 7. Thymol blue, 8 to 9.5. 8 to 9.5 is right in the middle of the limit. So thymol blue is the one to use. Bromothymol blue is a little bit low at 6. It's not quite started on the equivalence point. It's not quite started rising sharply. I'm going to go with thymol blue. Ethanoic acid is a weak acid. Sodium hydroxide is a strong alkali. The equivalence point when pH changes sharply is approximately between 7 and 10. So that's what I've said before. The uncertainty in the mean titer for the experiment is plus or minus 0.15. Calculate the percentage uncertainty for this mean titer. So that's how far it can be out. So I take that value, that's how far the titration could be out, 0.15, and I divide by the value of my titration. The value of my titration was 3.98 and I multiply by 100%. So I take the error, how far out it can be in centimetre cubed, I divide by the volume of my titration and multiply by 100. I could be 3.77% out. That's my percentage uncertainty. Suggest how using the same mass of ethanoic acid, so I'm using the same number of moles, the experiment could be improved to reduce the percentage uncertainty. So what you've got to do is, to reduce the percentage uncertainty, you've got to increase this value, this 3.98. That's the amount of sodium hydroxide that I've added to react with the ethanoic acid. If I make that number larger, 0.15 divided by a larger number will give a smaller percentage uncertainty. So I've got to increase the amount that I titrate. 3.98 isn't a very large amount to titrate of the sodium hydroxide. That's not a very large amount to come out of a burette. So how could I get more sodium hydroxide to come out of the burette? I would dilute it. So use a lower concentration of sodium hydroxide or dilute the sodium hydroxide, that would be fine, so that a larger titration is required. A larger volume from the burette is required. That's going to lower the percentage uncertainty in the titration. Question 3.1. Not too difficult a question, just unusual really. A peptide is hydrolyzed to form a solution containing a mixture of amino acids. So a peptide is a long protein chain formed together when amino acids join together in a condensation reaction, forming peptides, sometimes called amide links, carbon to oxygen and nitrogen to hydrogen link. and they can be hydrolyzed. In other words, the water can be put back, a reaction with water. You'll need some acid or some alkali to catalyze that reaction. This mixture is then analyzed by thin layer chromatography using a toxic solvent. So the solvent that's rising up the plate, the moving phase, is toxic and poisonous. The individual amino acids are identified from their RF values. The RF value is the height of the spot from the pencil line where it's been put onto the plate, divided by the distance from the pencil line up to the top of the solvent front, the top, the height that the solvent's risen to. Part of the practical procedure is given below. Parts of it are in bold text. For each of these parts, consider whether it's essential and justify your answer. So essential means it's either dangerous or the experiment would be ruined if you don't take note of it. So first of all, part 1, wearing plastic gloves to hold the TLC plate, draw a pencil line. So is it important to wear plastic gloves? The answer is, I would say it's essential, because you've got amino acids on your hand and that would ruin the experiment, that would contaminate the plate. The next part, a depth of no more than 1 centimetre cubed. In the developing tank, add the developing solvent to a depth of no more than 1 centimetre cubed. I think that means that if the pencil line is 1.5 centimetre cubed from the bottom of the plate, the depth needs to be below that. Otherwise, the solvent won't rise up the plate. It will just take the amino acids and just dissolve them into itself. So it's got to be below the pencil line for the experiment to work. I think that's essential too. If the solvent is too deep, it will dissolve the mixture from the plate. It needs to rise up the plate and carry the mixture of amino acids up with it. Place the TLC plate in the developing tank. Allow the developing solvent to rise up to the top. Remove the plate quickly. Allow the plate to dry in a fume cupboard. Is it essential to go to the top? Here, this is a bold part. No, it's not essential to go to the top. It's just better to go to the top. If it does go to the top, then your measurements are larger and you've got a less percentage error, but it's not absolutely essential for it to rise to the top of the plate. If it goes above the top of the plate, that would be essential, because you wouldn't have a measurement then, but it's not absolutely essential to go right to the top. It's just good practice. Allow the plate to dry in a fume cupboard. Yes, because the solvent's toxic, so that's essential. Outline the steps needed to locate the positions of the amino acids on the TLC plate and determine the RF values. Well, you're going to have to spray it with some kind of developing agent, or you can use ultraviolet light. So we use something called ninhydrin, which means that the amino acids show up on the plate, and therefore you can determine where they are, work out where they are, and then measure their heights and measure the height of the solvent front and calculate the RF values. So you measure the distances from the initial pencil line, that's where you place the mixture, and you measure up to the spots. You measure the distance from the initial pencil line up to the top of the solvent front, that's the height that the solvent's risen to, and you divide one by the other. So you take you divide the distance that the spots travelled divided by the distance that the solvent's travelled, and that will give you an RF value. Explain why different amino acids have different RF values. Well, it depends on their polar bonds. So different amino acids have different polarities, different size polar bonds. In other words, their delta plus and delta minuses are different. It depends on the differences in electronegativities between the atoms bonded together. So say, for example, if you've got an oxygen bonded to a hydrogen, or a nitrogen bonded to a hydrogen, then the oxygen, the hydrogen, or the nitrogen, the hydrogen are very different in electronegativity. So you get very large delta plus and delta minuses. You get very large polar bonds. And then you get hydrogen bonding as intermolecular bonding between those amino acids. So it depends on the polarities or the sizes of the delta plus or delta minuses in the amino acids. Then depending on how polar those bonds are, how large the delta plus and delta minuses are, then that determines how well they stick to the stationary phase. The correct word for stickiness or adhering is retention. Retention means that they've got large polar bonds and it sticks to the stationary phase. The stationary phase is the thin layer chromatography plate. So how well it sticks, or rather how much it retains, how much the retention is onto that plate. The larger the retention, the less it moves, and the smaller the RF value. Another way of saying it is that you could say how soluble it is in the moving phase. That's the solvent that's rising up the plate. The more soluble it is, then the further it goes up the plate. And usually that's determined on if something is polar, if the amino acid is polar, has large delta plus and delta minuses, it will dissolve in a solvent that's also polar, got large delta plus and delta minuses. It dissolves in there because you get intermolecular bonds set up. Question 4. A tricky question this, because it's for 6 marks and you've got to try and work out where the 6 marks come from. It's not scaffolded, so it's not broken down into sections. You've got to work out where you're going to get these 6 marks from. Ethane dioic acid is a weak acid, so let's have a look at it. 2 carbons, ethane, dioic, so it's got 2 carboxylic acid groups. And it breaks down, it shows you how it breaks down. What happens is that OH bond breaks. So we've got to work out how the structure of this supports that bond breaking. Look how it's broken. The oxygen has become minus and the hydrogen has become plus. So that OH bond, the electrons from the bond have moved onto the oxygen, have moved away from the hydrogen and onto the oxygen. Maybe that tells you something about the rest of this molecule, that it's helping to pull the electrons from along that bond onto the oxygen. Releasing H+, which would make it a stronger acid if they were to withdraw in that way. Use the concept of electronegativity to justify why the acid strengths of ethane dioic acid and ethanoic acid are different. Well, let's have a look at ethanoic acid. Ethanoic acid hasn't got the rest of this group here, it's got a CH3 group. So again, the OH bond has got to break. And the electrons have got to move onto the oxygen. But this CH3 here is not going to help because that repels electrons. It's going to push electrons the other way. So instead of moving the electrons onto the oxygen and releasing the H+, that CH3 is actually going to push them the other way and not move them onto the oxygen. It's actually going to push them onto the hydrogen. So let's have a look where some of these 6 marks come from. First of all, the first mark will come from the fact that it's saying that they've both got a COOH bond, COO, a carboxylic acid group, whereas ethane dioic acid has got 2 carboxylic acid groups compared to the 1 in ethanoic acid. That's where the first mark will come from. Both carboxylic acid group with COOH groups, but in ethanoic acid there's a CH3 and only 1 carboxylic acid group, but in ethanoic acid there are 2 carboxylic acid groups. So you'll get 2 marks for saying any of those 2 out of those 3. And then you've got to say that this part of the molecule in ethanoic acid has oxygens, and oxygens withdraw electrons. They're electronegative. So these carbon to oxygens and carbon to oxygen here and will pull electrons. So this section of the molecule will pull electrons towards itself and will help break that bond by moving the electrons onto the O, making O- and H+. So the oxygens in this section of the molecule here are very electronegative, and the oxygen atoms withdraw electrons. Whereas in ethanoic acid, the CH3, as I've said, is going to repel electrons, move electrons away from it, and actually won't facilitate, won't help breaking that bond. It will push electrons the other way rather than moving them onto the oxygen. The OH bond in ethanoic acid is more polarized. It means that the H+ becomes more delta plus. In other words, the electrons are being withdrawn, and this gets a large delta minus and a large delta plus, almost ready to break. There's more dissociation into the H+ ions. In other words, the OH bond is weakened and going to release H+, because this section of the molecule is withdrawing electrons. Very delta minus, very delta plus here, very delta minus, very delta plus, and the electrons will more likely move onto the oxygen and break that bond and release H+. So there's more dissociation. That means dissociation means breaking up of the molecule to make H+. And therefore ethane dioic acid is the stronger of the 2 acids. Question number 4.2. A buffer solution is made by adding 6.00 times 10 to the minus 2 moles of sodium hydroxide to a solution containing 1 times 10 to the 1 moles of ethane dioic acid. And it's giving you the equation here. So 1 mole of ethane dioic acid reacts with 1 mole of sodium hydroxide. They're the hydroxide ions produced by the sodium hydroxide. Okay, and it makes 1 mole of this ion and 1 mole of water. Okay, always the first step in this reaction is to work out the number of moles of sodium hydroxide and the number of moles of ethane dioic acid and subtract the two. Then if one reacts with 1 mole reacts with 1 mole, you can subtract the two to find out which one is in excess. Now first of all, you've been given the number of moles of each, so you've not been given a concentration or volume and have to work out moles, you've just been given them. And since 1 mole of this reacts with 1 mole of this, we can do a straight subtraction. So moles of ethane dioic acid and sodium hydroxide have been calculated for you, so that's fine. Which is in excess and by how much? Moles of sodium hydroxide is 0.06, 6 times 10 to the minus 2. Moles of ethane dioic acid is 0.1. 1 mole of that reacts with 1 mole of that. So we can just subtract the two and we can work out the ethane dioic acid is in excess by, because that's a larger amount, 0.1 is larger than 0.06. There's 0.04 moles of ethane dioic acid in excess. That will get you a mark for a start. Okay. The next part is to write an equilibrium constant. An expression for the equilibrium constant or the dissociation constant, same thing. The equilibrium constant for the acid or the dissociation constant for the acid. Okay, so this is the acid, ethane dioic acid, H2C2O4, and we know all acids make H pluses. Now, I could work out what was left, but I'm just going to call it X minus, that's fine. So I've got something else made, H plus and X minus. I could probably work out that it's HC2O4 minus by subtraction and working out what's left over. But I'm just going to call it X minus for simplicity. So, equilibrium constant equals the concentration of H plus multiplied by the concentration of X minus divided by the concentration of the ethane dioic acid. Remember at this point for a buffer you can't simplify, you can't say the concentration of H plus and X minus are the same, so you can't concentrate to you can't simplify to H plus, you can't do that for a buffer because you've sort of messed around with the amounts of these chemicals by adding some sodium hydroxide. So you can't do that. So we need to do something else. The next step then is to cancel a square bracket top and bottom. So you can cancel the square brackets around the X minus and cancel the square brackets on the bottom around the ethane dioic acid. Just leave H plus with the square brackets. You can do that incidentally because to turn concentration into moles you'd have to divide by the volume, and you'd be dividing by the volume in both cases. So you can cancel both of those square brackets on top and bottom. So now the dissociation constant, the ethane dioic acid, equals the concentration of H plus that's been left alone multiplied by not the concentration now but the moles of X minus divided by the moles of ethane dioic acid. Now what do I know? Well, I know the Ka. I've been given it 5.89 times 10 to the minus 2 or 0.0589 equals H plus concentration. I don't know that, and I know I'm going to have to work that out. If I can work that out, I can work out the pH quite easily. So I've got to find that. I don't know what moles of X is. I'll have to think about that in a minute. What's the number of moles of ethane dioic acid that I've got left over? Well, I worked that out in the previous part of my question, 0.04. So I've got 0.04. The only thing that's stopping me now from getting the concentration of H plus is the moles of X minus. And here's the trick. The moles of X minus equals the moles of sodium hydroxide in the initial part. You don't really need to know why. If you really wanted to know why, then X minus is made. It's this ion here, H2CO4 minus. That's the X minus. It's made when the sodium hydroxide and the ethane dioic acid react. So the number of moles of sodium hydroxide used equal the moles of X minus. But you don't need to know that. All you need to know is that you need to find this, and you look back and you find that's the number of moles of base or the number of moles of hydroxide in your original question. Now you've got that, 0.0589 equals H plus multiplied by 0.06 divided by 0.04. I would do that a little bit first, work out that it equals 1.5 and multiply 0.0589 by 1.5. And you get the concentration of H plus equals 0.039. The last part of this section is that pH equals minus log to the base 10 of the hydrogen ion concentration, so it equals minus log to the base 10 of 0.039, 1.41, which seems like a reasonable pH for an acid. Question 4.3. In a titration, the end point was reached when 25 centimeters cubed of an acidified solution containing ethane diuric acid reacted with 20.2 centimeter cubed of 2 times 10 to the minus 2 moles per decimeter cubed of potassium manganate 7. Now I've been given a volume and a concentration here of potassium manganate 7, so I can get myself a mark at some stage by working out the number of moles. But it also asks for an equation, and the equation I don't know, so I'm going to have to work it out. And with titrations such as this, you have to produce two half equations and then combine the two. Otherwise it's just too complicated to work out. So let's try and work it out systematically. Ethane diuric acid. Do I know the formula of ethane diuric acid? Yes, I do. It's H2C2O4 from the previous question. What do I know all acids make? All acids make H pluses. Well, there's two H's there, so it's going to make two lots of H plus. What have I got left over? C2O4. Now, with a little bit of thought, you could probably work out that it's going to make CO2 and 2 moles of CO2. That's a little bit of applied thinking here to think what might this make? And it makes carbon dioxide. Ethane diuric acid makes carbon dioxide. And then what I've got is I've made 2 pluses on the right hand side, so I'll need 2 electrons. Remember, half equations need electrons to balance them, because I've got no charges on the left and I've got 2 pluses on the right. I'm going to need 2 minuses on the right to cancel that out. Now potassium manganate 7 is MnO4 minus. You need to remember that, and you need to remember that it makes Mn2 pluses. So I've got MnO4 minus and I've got Mn2 plus. That's just something you need to learn. From that point onwards, you can work it out. To balance half equations, as well as needing electrons, you'll always need electrons, you can also use H plus and H2O to help you out. If I look at this equation here, I've got 4 O's on the left hand side and I've got none on the right hand side. So where are these O's going to go to? Well, they could go into waters. So I'm going to add some waters on the right hand side. I've got 4 O's, so I'll need 4 H2O's. The problem then is I've made 8 H's on this left hand side. What else can I use? Well, I can always use H pluses. So 8 H's, so I'm going to need 8 H pluses. You can always use H plus and 8 H2O's to help you balance half equations. Now, let's add up the number of minuses and pluses on the left-hand side. I've got 1 minus and 8 pluses. So I've got 7 pluses on the left, and I've got 2 pluses on the right. So it doesn't balance. 7 pluses on the left and 2 pluses on the right. I need 5 electrons on the left-hand side, because 7 pluses and 5 minuses now equal the 2 pluses that are on the right hand side. Now the problem, when I add these two together, I'm going to add everything on the left of this equation, everything on the left of this equation, everything on the right of this equation, everything on the right of this equation. So I'm going to everything on the left and everything on the right will come together to make one equation. So the problem is that I've got to balance the electrons. That's what I do. I create 2 half equations and then I multiply up to balance the electrons. What number can I multiply them by? Well, I could get these up to 10 electrons. 10 electrons, I think, is the lowest common denominator. So if I multiply everything through by 5 here, that will get me 10 electrons. So I multiply everything through by 5 and end up with 5 H2C2O4, 10 CO2, 10 H plus and 10 electrons. The other one to get to 10 electrons, well, I've got 5 electrons here, I can multiply that by 2. So I end up with 2 MnO4 minus, 8 times 2 is 16 H pluses, 10 electrons, 2 Mn2 pluses, and 4 waters become 8 waters. Now I add everything together, everything from the left, everything for the left of these two equations. So I've got 5 lots of H2C2O4 on the left with 2 MnO4 minus, 16 H plus and 10 electrons. There it is. And everything on the right, 10 CO2, 10 H plus, 10 electrons, 2 Mn2 plus and 8 H2O. And there it is on the right. Now, can I simplify things? I can cancel the electrons. That was the point of multiplying by some numbers to cancel, get the same number of electrons on each side. They need to cancel. And it looks as if I've got 16H plus here and 10H plus here. So I can take 10H pluses from each side and just leave 6H plus. So now I've got 5H2C2O4, 2 MnO4 minus, 6H plus, 10 CO2, 2 Mn2 plus, and 8 H2O. Without half equations, I would never have arrived at that equation. Okay, so what's next? So now I can work out the moles of potassium manganate 7. So I've got a volume 20.20 centimetre cubed. I need to get that into decimetre cubed. Centimetre cubed being a small unit into a larger unit like a decimetre cubed, I divide by 1,000, so that works out as 0.0202 decimetre cubed. Concentration equals moles divided by volume. Concentration equals 0.2, or 2 times 10 to the minus 2. 0.02 rather. 2 moles divided by 0.202, which is my volume. Moles are these two multiplied together, which equals 0.000404. I've got 0.00404 moles of potassium hydroxide. What am I going to do with that? I'm going to refer back to the previous equation. Now, for every 2 moles of MnO4 minus reacts with 5. Or another way of doing it is 5 moles of ethane dioic acid reacts with 2 moles of potassium manganate 7. Or I could say 2.5 of those, half the amount, reacts with 1 mole of potassium manganate 7, if that makes things easier. I haven't got 1 mole of potassium manganate 7, I've only got 0.000404 moles. So 2.5 moles of ethane dioic acid react with 1. So if I multiply this number by, 0.00404, that's the number of moles of potassium manganate 7 that I've got, by 2.5, I'll work out the number of moles of ethane dioic acid that I've got, 0.00101 moles of ethane dioic acid. Now I've got 25 centimetres cubed of it, or 0.025 decimetre cubed. Concentration is moles divided by volume. Moles is 0.00101 divided by the volume, 0.025 equals 0.0404 moles per decimetre cubed. I have now just worked out the concentration of ethane dioic acid as asked for in the equation. Question 5. A sample of ethane dioic acid was treated with an excess of an unknown alcohol in the presence of a strong acid catalyst. Well, a carboxylic acid group, COOH group, and an alcohol, OH, you will know make water. And that's what the strong acid catalyst does. The sulfuric acid helps to remove that water, and it will make an ester, a C double bond OO link. So the alcohol could react with the dioic acid on one end, or the alcohol could react with the carboxylic acid group not just on one end but on the other end as well. So that's why you could get 2 different products. If the alcohol reacts with just one end, you'll get one product. If it reacts with both ends, you'll get 2 products, a different product. So the product's reaction was separated and analysed in a time-of-flight mass spectrometer. It measures the mass of the products that are made. 2 peaks were observed, one at mass divided by charge ratio 104 and one at 118. Now these are the MRs. Assume the charge on the ion is 1+. These are the masses, these are the MRs of the 2 molecules. I'm guessing that this one will be if an alcohol reacts with one carboxylic acid group on one end, and if the alcohol reacts with both carboxylic acid groups to make an ester at either end, then it will make a slightly larger molecule. So let's have a little think. So what kind of alcohol am we going to make? 104 and 118. Well, the ethane dioic acid from the previous question, we know it's going to react with an alcohol to make an ester, and we know that ethane dioic acid is H2C2O4. Now, H2C2O4 is 2 1s for the hydrogens, 2 12s for the carbons, and 4 16s for the oxygen. It's got an MR of 90. So if the alcohol adds on and makes 104, it will release a little bit of water, but if it makes 104, and we've already got 90 from the ethane dioic acid, that doesn't leave a lot of mass for the alcohol. So I'm going to guess that it's methanol. And I guess that it's a very small alcohol because we've not got much MR left if we're going to get up to 104 from 90. So the methanol can react with one COOH group. We'll check out that it's 104 in a minute. We've got ethane dioic acid and the methanol. The O the OH on the carboxylic acid group reacts with the H on the alcohol, and it's going to make OOCCO, and then the OH has gone, and it reacts with that, joins on with that OCH3. So it's going to make that ester there, and water is released. So that ester there, with that OH gone from the carboxylic acid, and the H there, and the O bonds then onto the CO. So I've got C double bond O, OCH3 is my ester. Let's just check out what I've got. I've got 4 hydrogens, which is 4. I've got 3 carbons, which is 36, and I've got 4 oxygens, which is 64. That adds up to 104. So it was methanol. And then for my 118, it will react with both ends. So 2 lots of methanol. So at one end it loses an OH, and a methanol joins on, loses an H, and forms an ester at one end, and it will form an ester at the other end. And if I add the MR up of that, it will equal 118. Now, in a mass spectrometer, what you do is you fire an electron gun, use an electron gun to fire an electron onto this, and it will knock off another electron and leave this plus charged. So that's the ion that will be made in the mass spectrometer and will be accelerated along the tube. And we've got this ion then mass 104 and this ion mass 118. Since they've got a charge of 1 each, m divided by z, the mass divided by the charge, z is the charge, 1 equals 104 and 118. Outline how the time-of-flight mass spectrometer is able to separate these two species to give 2 different peaks. So it's because they've got different masses, and what actually happens is in the time-of-flight mass spectrometer, they've both got the same kinetic energy. So both of these molecules have the same kinetic energy, but because this one is smaller, and they both got the same kinetic energy, this one gets accelerated towards the plate more quickly and moves at a faster speed, gets accelerated more quickly, moves at a faster speed and hits the detector plate before this one, and that's why you can distinguish between the two. So the positive ions, these plus ions, are accelerated by an electric field to a constant kinetic energy, so they both got the same kinetic energy. The positive ions, both 104 and 108, have the same kinetic energy, but the ones at 104, mass 104, because they're smaller, move faster, and therefore the ion, the 104 ion, this ion, arrives at the detector before this ion, mass 118. Question 6. Which change requires the largest amount of energy? Well, the largest amount of energy is going to be the smallest atom, because it's going to have fewer electron shells, so less shielding. So helium is in period number 1. Yeah, it's the only one in period number 1, so it's going to be A. It's already lost 1 electron anyway, so it's only got 1 electron left. It only had 2 to start with. It's got an atomic number of 2. It's lost 1 electron. It's only got 1 left, and it's got 2 protons left. So it's got the same number of protons. Lost 1 electron, so only got 1 left, which will have so there'll be a strong nuclear attraction for that 1 remaining proton. So 1 remaining electron from the 2 remaining protons. It's got less shielding. It's A. A sample of 2.18 oxygen has a volume of 1870 centimetre cubed, a pressure of 101 kilopascals. I've been given a gas constant. So I've been given a gas constant and must be using PV equals nRT. Remember, pressure has got to be in pascals. So a large unit like kilopascals down into pascals, I'll be multiplying this number by 1,000. Remember, volume's got to be in meters cubed. Well, that's in centimetre cubed. Centimetre cubed up to the next unit, decimetre cubed, is divided by 1,000, and then decimetre cubed up to the next unit up, which is meters cubed, is divided by another 1,000. So I'll be dividing by 1,000, divided by 1,000 again to get this centimetre cubed up into decimetre cubed and then up into metre cubed. I've got a number of grams of oxygen gas. I'll need to know N, the number of moles of that. So moles is mass divided by MR, so that'll be 2.18 divided by the MR of O2. O2 is 2 oxygen atoms, each of mass 16, 2 16s are 32. So N is going to be 2.18 divided by 32, and I've got my gas constant. So let's work it out. PV equals nRT. P in pascals. I said kilopascals is a larger unit than pascals, so I need to divide by 1,000 to get it down into, sorry, multiply by 1,000 to get it down into pascals, so it's 101,000. Centimetre cubed up into the next unit, decimetre cubed, going larger is divide by 1,000, so that will be 1.870, but I've got to then get decimetre cubed up into the next larger unit, which is metre cubed, so I've got to divide by another 1,000, so it's going to work out as 0.0018 metres cubed, and 2.18 grams, number of moles is mass divided by MR, 2.18, the MR of O2 is 32, 0.068, so if I put that in then, pressure 101,000 multiplied by volume 0.0187 equals number of moles 0.068 multiplied by R, which is the gas constant 8.31, multiplied by temperature. I'm guessing I need the temperature. Yes, I need the temperature of the gas. It's going to be in Kelvin. All the answers are in Kelvin, so that makes it easy. I multiply these out first so I don't make any mistakes on my calculator. I multiply these two, 188.87. I multiply these two, 0.565, and I do that and I write that down at the side on my exam paper. Now then, temperature equals 188.87 divided by 0.565, 334, so my answer is B. Question number 8. An ester is hydrolyzed as shown by the following equation. So you've got an ester with a COO, a C carbon to oxygen double bond and then an O, and you've got a water molecule making carboxylic acid and an alcohol. It's the opposite of putting an alcohol and a carboxylic acid together and making water in a condensation reaction using a little bit of an acid catalyst. This time you're doing the opposite. You've got the ester, and now you're breaking it up, a process called hydrolyzing. Hydrolyzed means using water to break bonds, so now you're breaking up the acid to make the carboxylic acid and the alcohol again. We've got some groups on there, R and R dash. I'm guessing we'll never know what they are. They could be anything. What is the percentage yield of RCOH, so the carboxylic acid, made when 0.5 grams of RCOH MR100 is obtained from 1 gram of this RCOOR dash, this ester MR150. So let's have a look. We've got a gram, we've got grams, we've got mass, we've got MR. Clearly we want to work out moles. Moles is mass divided by MR. So we need to work out the number of moles of this that we've got made. It's obtained from 1 gram of RCOOR dash MR150. Clearly it wants us to work out the number of moles of this. So let's do that first of all. So moles of this made is, moles is mass divided by MR, 0.5 grams divided by 100, which is the MR, 0.005 grams. So I've made 0.005 grams of this. Again, do the same thing again for the RCOO. R for the ester that I'm starting off with is mass divided by MR, 1 divided by 150, 0.0067. So I've got 0.0067 moles of this. In the equation, 1 mole of this reacts with 1 mole of this to make 1 mole of the carboxylic acid and 1 mole of the alcohol. So if I've got 0.0067 moles of my ester, I should make 0.0067 moles of my carboxylic acid. So my theoretical yield, how much I should make if everything goes perfectly, is 0.0067. But I didn't, I only made 0.005 moles. So the amount that I made is much less than the amount that I should have made. So for my percentage yield, I take the smaller number, 0.005, that's what I did make, divided by my theoretical yield, what I should make, and multiply by 100, 74.6%, which is closest to 75%. The answer is D. A saturated aqueous solution of magnesium hydroxide contains 1.17 grams of MgOH2 in 100 centimeters cubed of solution. In the solution, the magnesium hydroxide is fully dissociated. That means fully split up into its ions. What is the concentration of Mg2 plus ions in the solution. But what have I got first of all? They've given me a formula. They've given me the molecular formula of magnesium hydroxide, so I could work out its MR. I've got a mass. Let's work out its MR and work out the number of moles of magnesium hydroxide that I've got. So MR, so I've got Mg is 24. Inside the brackets I've got an oxygen which is a 16 and a 1 for a hydrogen which is 17, but everything inside the brackets is times by 2. So I've got 16 plus 1 which is my 17, and I've got another 16 plus 1, add the 24, 58. So the number of moles of magnesium hydroxide that I've got is mass 0.00117 or 1.7 times 10 to the minus 3 divided by 58, which is my MR. I've got 0.000201 moles of magnesium hydroxide. I've got 100 centimeter cube solution, 100 centimeter cube, smaller unit into a larger unit like a decimeter cube, then divide by 1000, 0.1 decimeter cube. So my concentration of magnesium hydroxide is the number of moles that I've got, 0.000201 divided by the volume, moles divided by volume, 0.000201. Now, magnesium hydroxide, there's 1 Mg in there, and so 1 Mg will produce 1 mole of Mg will produce 1 mole of Mg2 plus when it dissociates into its ions. 1 Mg makes 1 mole of Mg2 plus. It'll make 2 moles of OH minus ions, but 1 mole of this makes 1 mole of this. So my number of moles of magnesium hydroxide that I have here equals the number of moles of Mg2 plus that I make. So it's the same. 0.00201 is the concentration of Mg2 plus that I'll make from MgOH twice. So that is another way of writing that is 2.01 times 10 to the minus 4. The answer is D. The rate equation for the hydrogenation of ethene. So hydrogenation is a reaction with hydrogen. Hydrogen adds across the double bond to make ethane. Is rate equals K multiplied by the concentration of ethene multiplied by the concentration of hydrogen. At fixed temperature, the reaction is compressed to triple the original pressure. So at fixed temperature, and basically they're saying that K, the rate constant, is remaining the same at fixed temperature. K only changes if the temperature changes. So the reaction mixture is compressed to triple the original pressure. So if you compress a gas to triple its original pressure, you make the particles into a smaller volume, a third of the volume. So if you compress it, you make it 3 times more concentrated. So your ethane's getting 3 times more concentrated, and your hydrogen's getting 3 times more concentrated. So your concentration of ethene is multiplied by 3, and your concentration of hydrogen is multiplied by 3. So that's multiplied by 3, that's multiplied by 3. 3 times 3 is 9. Your answer's B. When one molecule of ammonia is heated to a given temperature, 50% of the ammonia dissociates, means breaks down, and the following equilibrium is established. What is the total number of moles of gas in the equilibrium mixture? Oh, a tricky little question this. So 50%, 1 mole of this would make 0.5 of this, and 3 over 2 is 1.5. So 1 mole of this would make 0.5 moles of nitrogen and 1.5 moles of hydrogen. But you've not got 1 mole of this breaking down, only 50% of it breaks down. So 0.5 moles of this breaks down. So 1 would make 0.5 and 1.5. 0.5, only half of it, is going to make 0.25 and 0.75. Now the next bit is 0.25 and 0.75 equals 1, so you might think that the answer is 1. Now 1 doesn't appear, and the reason 1 doesn't appear is because 0.5 of this is left over, and 1 add 0.5 equals 1.5. Your answer is A. Question number 12. Which change would alter a value of the equilibrium constant Kp? Without even reading the question, the only thing that changes an equilibrium constant is temperature. That's the only thing that will change an equilibrium constant. So the answer is D, without even reading the rest. What is the pH of 0.02 mole per decimeter cube solution of a diprotic acid. Now, diprotic acid is an acid that produces 2 moles of H+. So 1 mole of the acid produces 2 moles of the H+, something like sulfuric acid. So if the concentration of the acid is 0.02, then the concentration of the H+ is double that, 0.04. Because 1 mole of the acid makes 2 moles of H+. So the concentration of the H+ is 2 times 0.2, 0.04, and the pH is minus log to the base 10 of the hydrogen concentration of the H+ concentration, and that will work out as 1.4, which seems like a perfectly good pH for an acid, which is B. Question number 14. The acid dissociation constant Ka of a weak acid Ha has a value of 2.56 times 10 to the minus 4. What's the pH of 4.25 times 10 to the minus 3 mole per decimeter cube solution of Ha? Right, the first thing I think I need to do is write an expression for Ka. So Ka is H plus concentration multiplied by A minus concentration divided by Ha, because Ha produces H plus and A minus. So that's the don't know why I've written it twice. That's the acid dissociation constant for Ha. So reminder again, Ha, all acids produce H+, so H+ must mean that A minus is left over. H+ multiplied by A minus, they're the products. Concentrations of each of those divided by the concentration of Ha is the equilibrium constant, or the acid dissociation constant. That equals 0.00026 or 2.56 times 10 to the minus 4. Now then, we can simplify this. There's no mention of the word buffer, so for every H plus that's made, 1 A minus is made, so the concentration of H plus and A minus are equal. So I can simplify that to H plus or H plus squared, because there's no mention of a buffer. I couldn't do that if it was a buffer. Divided by the concentration of Ha. Concentration of Ha is 2.56 times 10 to the minus 4. 4.25 times 10 to the minus 3 is the concentration of Ha. So I've put all those in. So H plus multiplied by H plus, these two values multiplied together, which is 0.000011. So H plus squared, or H plus multiplied together is this value. Square root it, 0.001 is the value of H plus, minus log to the base 10 of it to get the pH. It's 3. C is the closest. Answer C. Magnesium reacts with hydrochloric acid according to the following equation. A student calculated the minimum volume of 2.56 mole per decimeter cube hydrochloric acid required to react with excess magnesium to form 5.46 grams of magnesium chloride, MR 95.3. Well, first off, I've been given grams of magnesium chloride and I've been given MR. So while I've been given grams, a mass, and MR, they must want me to work out moles of magnesium chloride. So let's do that first. So moles of magnesium chloride is the mass divided by MR, 5.46 divided by 95.3. I've got 0.057 moles of magnesium chloride. Why have they given me an equation? Why do they want me to work out something to do with the hydrochloric acid? So 2 moles of hydrochloric acid make 1 mole of magnesium chloride. That's why they give me the equation, so I can work out molar quantities. So if I've got 0.057 moles of magnesium chloride made, I must have double the amount, 2 moles per 1, 2 moles of hydrochloric acid for every 1 mole of magnesium chloride made. If I multiply this value by 2, 0.114 are the moles of hydrochloric acid that I need. So what else have been given about the hydrochloric acid? I have got 2.56, I've got a concentration. So I've got the number of moles of hydrochloric acid needed, I've got the concentration of hydrochloric acid needed. Concentration equals moles divided by volume. Concentration is 2.56 equals the volume, moles, 0.114 divided by the volume. So I'll rearrange that so that volume, 2.56 multiplied by the volume is 114. So volume is 0.114 divided by 2.56, 0.0448 decimeter cubed, or 4.48 times 10 to the minus 2. They're all in decimeter cubed, so that's easy. 4.48 times 10 to the minus 2. The answer is B. Question 16. In which reaction is hydrogen acting as an oxidizing agent? Tricky question this. Cl2, so if it's just atoms on its own with no charge, then that's 0, and Cl goes to form Cl minus, and H usually goes to form H plus. So if Cl has gone to Cl minus, because that's an H plus, so this must be a Cl minus, and chlorine is in group 7 anyway, so gain's a minus. That's gone from 0 down to 1. Then the Cl has been reduced, so the hydrogen is actually acting as a reducing agent. Here, hydrogen turned a ketone into an alcohol. That is a reducing agent as well. So hydrogen turned a ketone into an alcohol. The ketone has been reduced to go into an alcohol. Here, nitrogen is 0. Hydrogen is usually +1, so that must mean that 3 + 1's, the nitrogen is in -3 oxidation state and gone down. So the hydrogen's acting as a reducing agent. The only thing here is sodium is in group 1, and sodium always forms +1, and then that forms the hydrogen into a H minus. So if the Na is +1, the hydrogen is a H minus, a hydride ion. That's sodium hydride. So that's just something to remember. Metals in group 1 like sodium and lithium, potassium, always form +1. So that's gone from 0 to +1. It's been oxidized, and the hydrogen has acted as an oxidizing agent. Answer D. In which reaction is the metal oxidized? Well, let's have a look. So the metal is copper. It's gone from 2+ here, and I is always -1, so the copper is always in +1. It's gone from 2+ down to +1 because I is always -1. Halogens are always -1, so that's +1, 2 down to 1+. That's been reduced. The Fe here, waters are zeros, so Fe is 3+, and Cl's are minuses, so waters are 0, so that's a -1. That must be 3+ to leave 2+ left over. That's not been oxidized or reduced, the Fe. CO, Cl4, Cl's are always -1, and that's 2-, so the CO must be in +2, because +2 - 4 leaves 2- left over. Copper's in +2, the cobalt's in +2 oxidation state. Water's a 0, 2+ left over. That's in 2+ oxidation state, so it must be D. Let's just check. S is in group 7, forms S2-. Mg is in group 2, forms Mg2+, gone from 0 up to +2. Yes, the answer is D. Mg has been oxidized. The following cell has an EMF of +0.46, so the reaction is going to go ahead if that's a positive EMF. Copper goes to Cu2+, so that's the way that it works, that this copper goes to form Cu2+, and Ag+ goes to form Ag. So the copper goes from 0 oxidation state up to +2 oxidation state. Let's have a look which is correct. Metallic copper is oxidized. Yes, it goes from 0 up to +2. So the answer is A. Straight off. Let's just check the others though. The silver electrode has a negative polarity. Well, Ag+ is going to form Ag. So the Ag+ is going to accept electrons, take electrons from the electrode. If it takes electrons from the electrode, the silver electrode is going to have a plus charge on it. So that's wrong. The silver electrode gradually dissolves to form Ag+ ions. Now Ag goes to form Ag. Ag+ goes to form Ag. It would form a coating of Ag on the silver electrode. The silver electrode will get larger and have more silver deposited onto it. Electrons flow from the silver electrode to the copper electrode via an external circuit. Now Cu goes to form Cu2+. In that process it loses 2 electrons, which would pass around to the other electrode that needs the electrons to form for Ag+, to accept them to turn into Ag. Your answer is A all the way. In an experiment, a group 2 metal 0.102 grams of X reacts with an excess of aqueous hydrochloric acid according to this equation. The volume of hydrogen gas given off 65 centimetre cubed. I've got kilopascal pressure, temperature in Kelvin. I've got a gas constant. I need to work out PV equals nRT for this hydrogen gas. PV equals nRT. Pressure is in pascals. It's in kilopascals. That's a large unit down into a smaller unit cell multiplied by 1,000, 99,000. The volume's in centimetre cubed. I need to get into metre cubed. To get into decimetre cubed and go up a unit, up to a larger unit, up to decimetre cubed, I'm going to divide by 1,000, and then from decimetre cubed up into metre cubed, up into the next unit up, and divide by another 1,000. So 65 divided by 1,000 divided by 1,000 is 0.00065 metres cubed. Okay, what's next? I've got the temperature, and I've got that in Kelvin 303, so I'm good. So PV equals nRT, pressure is 99,000 multiplied by volume 0.0065. N is the number of moles, which I don't know. 8.31 multiplied by 303 for the temperature. So 6.45 when I multiply these two together is N multiplied by 2517.93. Always useful to multiply your numbers out first, then you don't make a mistake. Then N is 6.435 divided by 2517.93, 0.00256 moles of hydrogen. Now I want to find out about X. That's why they've given me the equation, because 1 mole of X makes 1 mole of hydrogen. So the number of moles of X, the number of moles of hydrogen are the same. So the moles of X equals the moles of hydrogen. So the moles of X also equal 0.00256. I've been given a mass. Moles equals mass divided by MR. Moles 0.00256 of this metal X equals mass of metal X 0.102 divided by MR. Rearrange this equation, so MR equals 0.102 divided by 0.256. The MR of X is 39.84. If you look in a periodic table, 39.84, the closest what that one is to calcium, so your answer is B. Question 20. When a metal is 3+, oxidation state 3+, it's acidic. What it tends to do is it tends to withdraw electrons down the bonds of water onto the oxygen and release H+s. So with sodium carbonate, acids make carbon dioxide. So C or D are looking correct. So if it breaks down the sodium carbonate to make carbon dioxide, that can't then make gallium carbonate. It must make gallium hydroxide and carbon dioxide. So the clue is the 3 means that it's acidic, and it will make carbon dioxide, and the carbonate has broken down to make carbon dioxide. The hydroxide then comes from the fact that the gallium reacts with water, pulls the electrons down the bond onto the oxygen, releases H+, and leaves the OH- behind. But there's enough information without that to work out that your answer is D. Which compound gives a colourless solution when an excess of aqueous ammonia is added? Well, ammonia is basic, so it's an alkaline solution, so it tends to make hydroxide, so that will make magnesium hydroxide, which is a white solid. Aluminium will also make a white solid, aluminium hydroxide. Copper will make copper hydroxide, which is light blue, and then with excess it will actually make a deeper blue complex ion. The answer is B, and you may know that from the fact that silver nitrate is used to test for chlorides, bromides and iodides. So silver nitrate makes silver chloride, which is a white precipitate with any kind of chlorides. So silver nitrate and any kind of chloride makes silver chloride as a white solid, a white precipitate. Silver bromide is a cream precipitate, and silver iodides are a yellow precipitate. But then if you can't tell the difference between white, cream and yellow, then you add dilute ammonia. Dilute ammonia makes the silver chloride dissolve. So the ammonia solution dissolves the silver chloride. Dilute ammonia won't dissolve silver bromide and silver iodide. You need concentrated ammonia solution to dissolve silver bromide, and silver iodide doesn't dissolve in ammonia at all. So you can use ammonia to test for your precipitates of chlorides, bromides or iodides to double check whether they're white, cream or yellow. So your answer is B. Question 22. So what's the final species produced when an excess of aqueous ammonia is added to aqueous aluminium chloride? Well, ammonia solution is alkaline, so it's a weak alkali or a weak base, produces hydroxide ions from the water. So those hydroxide ions can replace the ligands. So aluminium AlH2O6 in water, that's the hexaqua ligand of aluminium, has 3 of them replaced because it forms a white solid, and with no charge. Something with no charge is not going to be ionic and not going to be able to intermolecular bond with the hydrogen bonds on the water. So that is something without a charge is going to be a solid. Ammonia and aluminium chloride forms a white solid, so your answer is obviously B. The following equation represents the oxidation of vanadium 4 ions by manganate 6 ions in acid solution. So we've obviously got to look at molar quantities here, 518,514, otherwise we wouldn't be given an equation. What volume of 0.02 mole per decimeter cubed potassium manganate 7 solution is required to oxidize completely a solution containing 0.01 mole of vanadium 4 ions? Well, there's the vanadium 4 ions. I've got 0.01 moles of vanadium 4 ions. I want to find out more about this MnO4 made from this KMnO4. So 5 moles reacts with 1. So I'm going to take that number 0.01 and divide it by 5. So it'll equal 0.002. And that will tell me that 0.002 moles of MnO4 minus are present. So I've got 0.01 moles of that. 5 react with 1, 0.001 divided by 5, 0.002 moles of MnO4 minus are present. Now I know the concentration here. So concentration is moles divided by volume. Concentration is 0.02. Number of moles is 0.002. Volume therefore is 0.002 divided by 0.02 is 0.1 decimeter cubed. It wants in centimeter cubed, that's fine. So decimeter cubed into a smaller value, smaller unit value of centimeter cubed. I'm going to multiply by 1,000. 0.1 times 1,000 is 100 centimeter cubed. My answer is D. Question 24. How many isomers have the molecular formula C5H12? So you could have pentane, 5 in a line. You'd have 4 in a line with a methyl group. The methyl group can't be at number 1 or number 4 because that would be pentane. And it doesn't matter whether it's at 2 or 3. 2 and 3, 2-methyl butane and 3-methyl butane are the same thing, just depending on which end you start numbering from. And then there's a third one which would be to go into a propane with 2 methyl groups, dimethyl propane. So your answer is 3, which is B. Which molecule is not produced when ethane reacts with bromine in the presence of ultraviolet light? Well, you should know that from a free radical reaction, hydrogen's never produced. If you've got bromine, it would make HBr. If you've got chlorine, it would make HCl. So you know that's a possibility. You know that on the ethane or the methane, that the H's get replaced by Cl's or Br's, depending on whether you're using bromine or chlorine. So that's a possibility. And you know that you might get some termination steps where you get some molecules reacting together. So that's a possibility as well. But at no point do you ever get hydrogen. Let's have a look at the free radical steps then. So your answer is C anyway. Bromine produces 2 bromine radicals. Ethane then with a bromine radical forms CH3CH2 dot or C2H5 dot. Better if you put CH3CH2 dot and the dots on the C. The C that hasn't got enough bonds and makes HBr. So HBr or HCl, depending on whether you're using bromine or chlorine, is always made. So B is an obvious given. It can carry on reacting, and so it could make CH4Br2. That's a possibility. And then at the end, if you've got some CH3CH2 dots, they could react together to make butane. So all of those are possibilities. Hydrogen stands out as the one that's never made in a free radical reaction. 26. How many structural isomers have the molecular formula C4H9Br? So what you've got is you've got butane, or you could shorten the chain. Butane to start off with, let's say, with a Br. So where could the Br be on butane? It could be at carbon number 1, or it could be at carbon number 2 to make 1 bromobutane or 2 bromobutane. 3 bromobutane is the same as 2 bromobutane, just labelled from the other end, and 4 bromobutane is the same as 1 bromobutane, just labelled from the other end. So I've got 2 from a butane chain. I could shorten the chain to be 3, and I could have methyl propane, and then the Br could be at carbon number 1 or carbon number 2, so that's 2 more. So there's 4 in total. If it was if the Br was on carbon number 3 of methyl propane, it would be the same as 1 methyl propane. So I can have 1 bromobutane, 2 bromobutane, 1 bromomethyl propane, and 2 bromomethyl propane. The chain can't get any shorter than that, shorter than 3 with a branch. So my answer is C. What's the major product of the reaction between but1ene and dBr? Well, D is representing a different kind of hydrogen. So if you imagine D is HBr and you've got but1ene, so you've got the carbon-to-carbon double bond between carbons number 1 and carbon number 2. Let's imagine it was HBr for a start. The H would go on to carbon number 1 and leave a secondary carbocation, which is more stable, and the Br then would join onto carbon number 2. If the H went on to carbon number 2, it would leave a primary carbocation, which would be less stable. So the major product has the H adding on to carbon number 1 of the but1ene. The carbon-to-carbon double bond is between carbon number 1 and carbon number 2, and so the H will go on to carbon number 1, leave a plus charge, a secondary carbocation with a plus charge on carbon number 2, and the Br minus will use its lone pair of electrons to then react with that C plus carbocation and form the Br on carbon number 2 in a process called electrophilic addition. So I'm looking for the D on carbon number 1, which represents the hydrogen, and the Br on carbon number 2. That's the D on carbon number 1, the carbon on number 4, the D on carbon number 1, and the Br on number 3. Here, it's labelling from the other end, but the D is on carbon number 1 and the Br is on carbon number 2. So C is looking good. Let's just check D. Yes, D is the other way around. That's the minor product, where the Br is on carbon number 1 and the D is on carbon number 2. So your answer is C. Number 28. Why are fluoroalkanes unreactive? You either know this or you don't. The answer is that the CF bond is very strong. So if you had something that was, say, for example, an OH minus, and you're expecting it to the fluoroalkane to undergo nucleophilic substitution with the OH minus attacking the delta plus on the C and expecting the electrons to go from the CF bond onto the F and release F minus. It's just not going to happen because that bond is too strong. So your answer is D. Which alcohol could not be produced by the reduction of an aldehyde or a ketone? Well, if you think about it the other way around, then an alcohol, a tertiary alcohol, can't be oxidized by acidified potassium dichromate to form an aldehyde or a ketone. So a tertiary alcohol can't work, and the reason is that if it's a tertiary alcohol, then the carbon with the OH has got 3 other bonds attached, and therefore when it forms a double bond to an oxygen, it would have 5 bonds. Then it would have 3 carbons still bonded and a double bond to an oxygen. It would have 5 bonds. That's not possible. So if you look at it the other way around, if you had an aldehyde or a ketone, you're expecting the carbon to oxygen double bond to become an OH and the carbon to get an extra H. If it's got 3 other carbons already bonded to it and it forms an OH and an H, it's going to have 5 bonds. So another way of looking at it is that if it's got 2-methylbutan-2-ol, if the numbers are the same, then the ol group is at carbon number 2 in the middle of a chain, there's a methyl group at carbon number 2. So that carbon number 2 has got a carbon either side and a methyl group and an OH. How could that possibly have formed that ol from a carbon to oxygen double bond? Because that carbon number 2 would have to have a carbon to oxygen double bond before it was reduced to become an OH, and it would have 3 other carbons around it. It'd have 5 bonds. It's not possible. So you're looking at this is a tertiary alcohol, couldn't be oxidized to form an aldehyde or a ketone, and vice versa, the aldehyde or a ketone couldn't be reduced to make a tertiary alcohol in the other direction. Question number 30. Which compound forms optically active compounds? That's something with a chiral carbon, a carbon with 4 different groups around it that would rotate plane polarized light in different directions because it's got 2 enantiomers, unless of course it was a racemic mixture with equal amounts of the 2 enantiomers. So we're looking for a chiral carbon on reduction. Reduction is reaction with hydrogen. So what would happen on A? There's a double bond there, so if hydrogen were to join onto here, this side of the double bond, this carbon or this carbon, then this carbon would have a methyl group, an H. This one would be CH2CH3. Oh, on this side there'd be CH2CH3. So that carbon would have a methyl group, a CH3, an H, a CH2CH3 and a CH2CH3. It's got 2 groups the same. It's not A. B. If you added hydrogen across this double bond, then this carbon could potentially be a chiral carbon, except that that would be CH, CH2CH3, CH, CH2CH3, CH, and this one would gain a hydrogen as well across the double bond. That would be a CH3. Now that carbon would have 2 methyl groups, a CH3 and this one when it became a CH3. C. Well, C is potentially an idea. So when that aldehyde, when that ketone is reduced with hydrogen in the presence of something like a nickel catalyst would work, then you get that converted into an OH and an H. But that carbon there would have 2 methyl groups, so that oxygen would become the ketone would become reduced into an OH and an H, but the 2 methyl groups would mean that that one wouldn't be a chiral carbon, whereas this one would be. Butanone could be, because when that O becomes an OH and an H by reduction with something like hydrogen and a nickel catalyst, or something like sodium borohydride would be another reducing agent, that would become an OH. There'd be an H on there, it'd have a methyl group and an ethyl group. Your answer is D. How many secondary amines have the formula C4H11N? Tricky question this. The N has got to be bonded to 2 other carbons. That's what a secondary amine has. A primary amine has the N bonded to 1 carbon, the secondary amine has the N bonded to 2 carbons, and a tertiary amine has the N bonded to 3 carbons. So it's got to be bonded to 2 carbons. It's got to be in the middle of this chain. If it was at the end of the chain, it would only be bonded to 1. So this C4H11, how could it be? Well, if it was 4 in a line, the N could be between carbon number 1 and carbon number 2. It could be between carbon number 2 and number 3. That would be a possibility. If it was in between carbon number 2 and number 3, so yeah, that's the only way, isn't it? So between 1 and 2, it could be between 1 and 2. It could be between 2 and 3. 3 and 4 would be the same as between 1 and 2. However, you could have 3 in a line with the nitrogen still in the middle, in between carbon number 1 and carbon number 2, and a methyl group at carbon number 2. It's B. So your answer is B. Let's have a look again then. So you've got 3 in a line, a nitrogen, and then a 4th one there, so that's in the middle. You could have 2 in a line and the nitrogen, and then 2 more, so that's in the middle. If the nitrogen were here, in between these 2, it would be the same as between those 2. But you could have a branch, so C, N, H, C, and then 2 branches, 2 methyl groups, so a chain of 3 with the nitrogen in between carbons number 1 and carbon number 2, and a methyl group on carbon number 2. So your answer is B. Question number 32. Which compound has the highest boiling point? So immediately I'm trying to find hydrogen bonds. I'm trying to find a nitrogen bonded to an H, an oxygen bonded to an H, or an F bonded to an H. There's no N's, F's, or O's in that, neither for that. Oh, there's an N bonded to an H there. That would have hydrogen bonding. That's going to be probably my answer. There's an F bonded there, but it's CH3F. The F is bonded to the C, so I've not got a hydrogen bonded to an F. C is my obvious answer. Which compound can polymerize with itself? So what it's got to have is it's got to have one group at one end and a different group at the other end, two different groups at either end, and the one group at the one end can bond to the other group at the other end and form a polymer. So what kind of groups are we looking at? Well, you could have a carboxylic acid group with an OH, except that's two carboxylic acid groups, that's not two different groups. You'd have a carboxylic acid group with an OH, would form an ester. You could have a carboxylic acid group with an NH2, which would form an amide, a polyamide. You could have an acyl chloride, a COCl, maybe with an NH2, that would form hydrogen chloride and would also form a polyester. Not got two different groups. Well, not got a group really that will work. Got two carboxylic acid groups here. We've got an acyl chloride at this end and we've got an NH2 group at this end. So these would keep reacting with each other, and that would form CONH. It would form a series of peptides or amide links and release HCl in a condensation reaction. Your answer is D. Question 34, a very straightforward question except it's worded really badly. A drug is designed to simulate one of the following molecules that adsorbs onto the active site of an enzyme. Which molecule requires the design of an optically active drug? So it basically means that one of these is optically active, and the drug that's going to go with it, that's going to simulate it, is equally got to be optically active. So it's basically saying which of these is optically active, which of these has a chiral carbon, which of them has four different groups attached to any one carbon. That carbon there has got an H and an H now, that's got two H's, and that one hasn't got four bonds. Three H's, that one hasn't got four bonds, that hasn't got four bonds. This one's a possibility. Carbon with a hydrogen, carbon with an OH, carbon with a methyl, carbon with a carboxylic acid group. Your answer is C. This one, two H's, no, two H's, not got four bonds. Your answer is C. It's the only one with a chiral carbon. Question 35. Which amine has only three peaks in its proton NMR spectrum? So proton means hydrogen. Three peaks, three different peaks means three different hydrogen environments. The easiest way to do this, you're not going to do this without drawing them out, so let's draw all three out. So methylamine has got a CH3 with an amine, an N, and therefore it's got to have two H's on it, because there's a methyl and then an N, and then the N has got to have three bonds, one bond to the carbon and then two H's. Trimethylamine, so three methyl groups, three methyls around an N, so that's a tertiary amine with three methyl groups off the N. Diethyl, an ethyl is a CH3CH2, it's got two of them, diethyl amine, so the N is bonded to a carbon and another carbon to the two ethyl groups, and it's got one H. And the propylamine is got three carbons in a row, bonded to the N, and the N then has got a propyl group and then two H's. The H's contribute as well to the proton NMR, so let's count up the number of different hydrogen environments. To make it easier to see, I've colour-coded them. There's three H's there bonded to the same carbon, I've called them red. Two H's bonded to the N, I've called them blue. Two different colours, two different carbon environments, the answer is not A. Each of those methyl groups, all the three methyl groups are bonded to the same atom to the N, so they're all equivalent. So all of those hydrogens, three lots of three, all those 9 hydrogens are all equivalents. That would produce one peak, so 2 peaks and one peak. Answer number C. Let's have a look here. So we've got two ethyl groups. The two ethyl groups are equivalent because they're both bonded to the same end, so they're both identical in that respect. The H's are different from the CH2s, so let's call those red, let's call those blues, and we've got an NH here because it's bonded to 2 ethyl groups. It needs a third bond in H. There's 3 colours there, so that'll produce 3 peaks, 3 different hydrogen environments. Let's just check D just to be sure. CH3, CH2, CH2, those two are different colours, a blue and a sort of brown colour there. I've labelled it because that CH2 is joined to an N, whereas this CH2 is joined to a CH3 and a CH2. So those two are different environments. And then you've got the N bonded to one of the carbons of the chain at the end of the chain, in NH2. So I've got 4 different peaks there. So I've got 2 peaks on A, 1 peak on B, 3 on C, 4 on D. The answer is C.